Now, the first thing we're going to do is we're going to develop a key. In pink, I have made a plus sign. That pink plus sign is going to represent a proton, of course. And here, I'm using the actual symbol for an electron that's used by scientists, and I wrote it in green. That's E minus, and that, of course, is an electron. And then finally, neutrons have zero net charge. They're neutral, and so I have a 0 here to represent the neutron. Now, these are the 3 subatomic particles that you need to know about in this course. So I'm going to again emphasize that the protons and the neutrons will be found in the nucleus, and the electron will be found in the shells. Now, what are the shells? Well, the shells are just regions that are a distance from the nucleus. And interestingly enough, the shells are arranged in such a way to try to jam as many electrons in there as possible. But the first shell, being really close to the nucleus, doesn't have a lot of room. So the rule for the first shell is that it can hold up to 2 electrons. And so I'm just going to write 2 E minus because that's what scientists do. And then the second and the third shells are farther away, and they have some different shapes. And so each one of them can carry 8 electrons. Now, if we wanted to, we could go on and on here. We could tell you what that the 4th shell has 18, the 5th shell has 32, and so on and so forth. But right now, we're going to focus on drawing the low mass common elements, because frankly, no matter how you draw an element, the heavier it is, the higher its atomic number, the more difficult it is to draw. And so we'll start with the simple ones. So again, here's our periodic table. And if we look for the element lithium, we will find it in group 1A underneath hydrogen, and it has an atomic number of 3. The upper right-hand corner, you can see that there's a 3. Underneath that, there's sodium, whose atomic number is 11, and then potassium, whose atomic number is 19. But we're just looking at group 1A right now. All right, on the opposite side, we have this group, which is the halogens, and so fluorine is 9, and chlorine is 17, and bromine is 35. You probably notice they all end in I and E. Okay, so what we're going to try to do is we're just going to try to draw something. So I'm going to start off with lithium, and the symbol for lithium is Li, and I'm going to write the atomic number of lithium above it. I'm going to make a little box. Now, since I know that lithium has an atomic number of 3, I know for a fact that it's going to have 3 protons in its nucleus. So taking my little red pink pen, I'm going to make 3 little plus signs. And they represent the 3 protons in a lithium nucleus. Now, the normal rule is the neutrons are kind of like glue, and you normally need at least 1 neutron for every proton you have in the nucleus. Sometimes you need extra neutrons to make a stable nucleus, but with the low mass elements, it's fairly common that the simplest way is where you have exactly 1 neutron for each proton. And so I made 3 pink plus signs for my protons, and I made 3 little zeros for my neutrons. Now, what I'm going to do is I'm going to make a circle around that, and that represents the atomic nucleus. And again, I want to be very clear with you. This is sort of a lie. It's flat and 2-dimensional, and I'm making the atomic nucleus really big so we can put a little detail inside of it. But keep in mind that the actual atomic nucleus would only be 10,000 to 100,000 times smaller than the atom itself. Okay, so protons and neutrons belong in the nucleus. Now it's time to put the electrons. So we're going to make a neutral lithium atom. Since it's going to be neutral, that means the number of electrons, which have a negative charge, is going to have to equal the number of protons in the positive charge. You might think, well, let's make a shell, let's put 3 E minuses on it. However, the first shell can only hold 2. So I make another little circle, and this represents the first shell. And what I'm going to do now, the eraser is so helpful. What I'm going to do now is I'm going to put 2 electrons on that first shell. E minus, E minus. Okay, so lithium's atomic number is 3. I want this to be a neutral atom, so I need 1 more electron. That means this one shell is not enough. And so I'm going to make a second shell. And the question is, how many more electrons do I need? And you should be able to see that the answer is just 1 more. So I'll just make a spot anywhere, really. And now I do this. But I'm not quite done drawing this second shell, because the second shell says there's room for 8 electrons on the second shell. But I'm only drawing in 1, because that's all we need. So I have to do one more thing. 1, 2, 3, 4, 5, 6, 7. I'm going to make some circles on the outer shell. In fact, I'm going to make 7 of them to show that I have 7 unfilled spaces. I've got 1 filled space, which is this sole electron on the outer shell. And then I have 7 other spaces, 1, 2, 3, 4, 5, 6, 7, that represent the unfilled spaces. So it's going to be really, really important, ladies and gentlemen, that when we're talking about this, that we get the electrons, the arrangement of electrons right. And it's really important to get the arrangement of electrons on the outside shell right, because the fact that there's 1 electron here, 1 filled space, and 7 unfilled spaces. Most chemistry is based upon the arrangement of the electrons in the outer shells, which in turn is based on an attempt to try to balance the positively charged protons found in the nucleus. So this is the Hatfield way to draw atoms. Pink plus signs, pink or red for protons, zeros for neutrons. Both of these are found in the nucleus. Then we use the symbol that scientists actually use for the electron, which we arrange in shells outside the nucleus. The first shell can hold a maximum of 2. The second and the third shell can hold as many as 8. And we begin by just getting the atomic number. The atomic number will tell us the number of protons. Now, I'm just going to test your brain a little bit. Let's suppose that instead of me giving this to you with the element name, suppose I just gave you a drawing and asked you to tell me what element it was. Can I do that? I sure can. I sure can. So I'm about to erase the symbol for lithium. And then I'm going to erase the drawing for lithium. I'm going to make another drawing. And it would be nice if you could follow along and tell me after I make the drawing what element it is. Of course, to figure that out, you'd need to look in your periodic table. So here we go. I'm making a drawing, starting with the nucleus. My neutrons. Now I use plus signs for the protons. Okay. Big circle around the nucleus. Okay, now I'm going to have my first shell. Well, I've got 6 plus signs. So I am definitely going to need to have that first shell, which is definitely going to be full. That's 2. Now I've got 1, 2, 3, 4, 5, 6 positive charges. So I'm definitely going to need another shell. So since I already have 2 negative charges, to balance the 6 positive charges, I'm going to need 1, 2, 3, 4 more electrons, which means I'm going to have 4 filled spaces on the outer shells. And since there's room for 8, that means I'm going to have 4 unfilled spaces on the outer shells. Again, I encourage you to copy that diagram down, and then I would encourage you to use your periodic table and figure out which element this is. And I'm going to leave this illustration up for perhaps, 30 or 40 seconds. And then I'm going to erase it. I'm going to show you something else that you're going to need for your next assignment in this course. Well, Miss Gutierrez, very good for you. That's very good. And how do you know that? If your answer is correct, why would that be the correct answer? How did you determine it? There's actually a couple different ways you could answer that question. I'll let you think about that. I'm going to leave this up on the screen for about 20 more seconds. Now, I want to emphasize that the way I'm drawing an atom here is flat and two-dimensional. The nucleus is greatly exaggerated. And of course, these are just abstract symbols. The atom doesn't actually look like this. It doesn't look like anything at all. It's smaller than light. We're just trying to be realistic with you. But a lot of times in science, we don't tell you the full truth. We give you a simplified version to help you understand the basic concept. And so it doesn't mean that we're trying to lie to you, but sometimes later on, when you find out the real model and it gets more realistic, you think, man, why didn't they tell me that before? And I kind of feel that way too. So what I've done is I've told you up front that the way I draw atoms is kind of cartoony and unrealistic, but I'm also telling you that every attempt to make an actual picture of the atom is also cartoony and unrealistic. And if you understand that, we're not really lying to you. We're giving you the information in an abstract form to help you get a deeper understanding of what's actually going on down there in the world of the atom, in the world of the tiny, tiny